So in this lecture, I will discuss infinitely divisible laws. Actually, we want to consider the following problem, which I mentioned already. We have an array of independent random variables, so xn1 up to xn kn, where kn is a sequence converging to infinity, and these variables are independent. And we would like to consider the convergence in distribution of the sum of these variables. So we would like to study, well, to obtain, to derive sufficient conditions for, say, Sn minus an, a sequence of real numbers, to converge in distribution to some random variable. Of course, we need to impose some conditions on these variables. So one condition is the, well, uniform smallness or uniform negligibility, which means that if you take the probability that x and j it's larger than epsilon, the maximum over j of this quantity, j running from 1 to kn, you would like this sequence to converge to 0 for all epsilon positive. So we will always impose these conditions, which means that they are small and uniformly small, since we are taking the maximum, and we would like to consider this problem. We can understand the central limit theorem, which was proved in the previous lecture, as a preliminary problem in which these variables had special forms and they had expectation equal to 0 and finite variance. So here, observe that I will not impose anymore the random variables x and j to have finite first and second moment. The only condition I will be imposing is this one. And before investigating this general question, I will start by considering Poisson limits. So in order to investigate this problem, let's first consider another type of asymptotic behavior of such a sum. We have seen the central limit theorem in which the limit was a Gaussian random variable. So now we will see another type of assumptions which provides convergence to Poisson law. So let me take, in this respect, kn equal to n, and a sequence xn1, xnn, which are IID, random variables, with the following distribution. Well, these variables take only the value 0 and 1, so they are Bernoulli. The probability that x and 1 it's equal to 1 will be represented by Pn, and this is 1 minus the probability that x and 1 it's equal to 0. Now, well, what is the probability? So you see, this maximum does not depend on j, because all these variables have the same law. So what is the probability that x and 1 it's larger than epsilon? Well, let's say if we take epsilon larger than 1, then this probability is 0. If we take epsilon between 0 and 1, so this is equal to the probability that x and 1 it's equal to 1, and this is Pn. So in order for this assumption to be satisfied, what we will impose here is that this sequence Pn converge to 0. If this sequence Pn converge to 0, then this uniform smallness condition is satisfied. And now let's see what is Sn. So Sn will be the sum from 1 to n of x and j. And I want to investigate the convergence of this sequence in distribution. So I want to find conditions on the sequence Pn for which this sequence converge in distribution. My observation is that Sn, for all n, take only non-negative integer values, so that the probability that Sn belongs to n union 0, that this is equal to 1 for all n. And therefore, for such a type of discrete random variables, Sn converge in distribution if and only if the probability that Sn is equal to k converge to some q of k for all k. So let me call this set n0. And if q is a probability measure on the set n0. So Sn will converge in distribution if and only if the sequence converge to a probability measure on n0. So let's compute what is the probability, for instance, that Sn is equal to 0. So the probability that Sn is equal to 0 is the probability that the sum is equal to 0 and since these random variables x and j take only two values, 0 and 1, this sum is equal to 0 if and only if they are all equal to 0. So px and j is equal to 0 for j between 1 and n. But these random variables are independent, so the probability of this intersection is equal to the product of the probabilities, and they have all the same distribution. So this is equal to the probability that xn1 is equal to 0 to the power n. And by definition, this is 1 minus Pn to the power n. So we would like this sequence to converge to some q of 0, and for this sequence to converge, I will write it as 1 minus n times Pn divided by n to the power n. So let me call an n Pn. So this is equal to 1 minus an divided by n to the power n. And what I claim is that this expression converge if and only if an converge to some lambda in 0, 1, in 0 infinity. So my claim is that if an converge to a lambda, which belongs to the interval 0, infinity, closed at 0, then this expression converge to exponential minus lambda, and if it converge, then an converge to lambda. So if this expression converge to something, of course this is non-negative, so the limit will be non-negative and can be written as the exponential of minus lambda. If this expression converges to exponential minus lambda, then this means that an is converging to lambda. So I leave it to you as an exercise to prove this condition, and therefore we have at least one requirement on the sequence Pn. We need nPn to converge to some lambda in this interval. So next, what I will claim is that, well, if n times Pn converge to some lambda, then the sequence Sn is converging to a Poisson distribution with parameter lambda, and conversely, if Sn converge in distribution to some distribution, then nPn converge to lambda, and this distribution is a Poisson of parameter lambda. So this is the next result. So remember the context. We have an array of IID random variables for each n, we have n IID random variables, and they have a Bernoulli distribution with parameter Pn. This means that the probability that xn1 is equal to 1 is Pn, and the probability that xn1 is 0, it's 1 minus Pn. And here we are assuming that Pn is converging to 0. And my claim is that if Sn, and here Sn is equal to the sum of these random variables, x and j going from 1 to n. So if this sequence is converging in distribution, this happens if and only if n times Pn is converging to lambda, where lambda is a non-negative real number. And in this case, the limit, which I'm representing by S, it's a Poisson distribution of parameter lambda. So let me first recall what is a Poisson distribution of parameter lambda. So let's say that X has a distribution of Poisson. This means that the probability that X is equal to K, that this is equal to lambda, which is this parameter, K factorial exponential minus lambda. And here I'm assuming that lambda is strictly positive. If lambda is equal to 0, then this means that the probability that X is equal to 0, it's 1. See that for K equal to 0, this is 1, while for K larger than 1, it's simply 0. So this is a degenerate distribution. So usually we will assume that lambda is really positive, but in this proposition, we need to consider the case in which lambda takes the value 0. So this is the distribution, and this is what this is the proposition I want to prove now. So let's first show one direction. And as we have seen, if I want to prove, so let us assume that nPn is converging to lambda, which is a real number between 0 and plus infinity. And to prove that Sn converges to a Poisson distribution, what we need to show is that the probability that Sn is equal to K, that this converges to the probability that X is equal to K, and this we have seen is lambda to the power K divided by K factorial exponential minus lambda. If lambda is really positive, otherwise it's 0 if K is different from 0, and it's 1 if K is equal to 0. So let's compute what is the probability that Sn is equal to K. Sn is the sum from 1 to n of x and j, and this equal to K. So what we have here is that we have n positions, 1 to n. In these n positions, we have K positions in which we have a 1, and therefore n minus K positions, which takes the value 0, and this because x and j takes only values 0 and 1. So for this sum to be equal to K, this means that they have K of them have value 1, and the others have value 0. Now, what is the probability? Well, if you take any possible vector in which you have k1s and then n minus k0, the probability of such a vector, since they are all independent, well, it's the probability to have 1 k times, and this probability is Pn. So that will be Pn to the power k, because 1 appears k time, and the probability of having a 1 is Pn. Then we have 1 minus Pn, which is the probability to obtain a 0 to the power n minus k, because, well, there are n minus k positions in which we have a 0. And then we have to count the number of vectors, the number of sequence in which we have k positions with 1 and the others with 0. And this is, well, there are n positions. We choose k of them to get to place a 1. So there are n choose k possible vectors or possible different combinations of vectors. So this is the probability that this sum is equal to k. It's n choose k times Pn to the power k, 1 minus Pn to the power n minus k. So k it's fixed, n it's converging to plus infinity, and mind that I replace n by the capital N. So n, capital N, and n are the same object. So here, since n is converging to plus infinity, what we have is that I will rewrite this object as 1 over k factorial, and then we have n times n minus 1 times n minus k plus 1. So this is n choose k, and then we have Pn to the power k, and 1 minus Pn to the power n minus k. This 1 minus Pn to the power k, okay, I will rewrite this expression. So I'm assuming here, remember that nPn it's converging to k. So what I will do, I'll keep this 1 over k factorial. Then here we have k terms. I will divide these k terms by n. So we have 1. Then we have n minus 1 divided by n up to n minus k plus 1 divided by n. Now I have k terms, so here I divided by n to the power k, so I get n to the power k on the numerator, which will I add with Pn. So that gives me nPn to the power k, and that will converge to lambda to the power k. And here I will write this expression as 1 minus Pn minus k, and then 1 minus Pn, I will write it as n times Pn divided by n, and this to the power n. And now I will take the limit in each term. So this is converging, and let me write here the limit. We have 1 over k factorial. Each of these terms is converging to 1. We have 1 minus 1 over n, 1 minus k minus 1 over n, so they're all converging to 1. nPn, it's converging to lambda, so this gives me a lambda to the power k. Pn, we know that Pn it's converging to 0, so 1 minus Pn minus k, this is converging to 1. And finally, as I mentioned before, since nPn is converging to lambda, this expression is converging to exponential minus lambda. And you see that this is exactly, so let me assume first that this lambda is strictly larger than 0. We will consider the case in which lambda is equal to 0 after, by considering the same expression. So this is converging to this expression, and this is exactly the probability that a Poisson, if x it's a random variable whose distribution it's a Poisson of parameter lambda, this is exactly the probability that x is equal to k, and therefore, indeed, we prove that the probability that Sn is equal to k converges to the probability that x is equal to k for all k, and this means that indeed Sn is converging in distribution to a Poisson distribution of parameter lambda. So let's see the case in which lambda is equal to 0. Well, if lambda is equal to 0, so now let me consider the case in which lambda is equal to 0. The computation we did holds up to this identity. Now I will observe that if I'm taking k equal to 0, if I take k equal to 0, this is 1. This is 1 also. We have here, well, if k is equal to 0, these terms, so maybe let's go back to this identity here. If k is equal to 0, so this is just 1, this is 1, and this is 1 minus Pn to the power n, which I'm writing as 1 minus Pn times n divided by n to the power n, and this is converging to exponential minus n lambda by the previous argument, but now lambda is equal to 0, so this is 1. So if lambda is equal to 0, what we just showed is that the probability that Sn is equal to 0 converges to 1. So in our case, maybe let me write it in orange somewhere. What we proved is that if lambda is equal to 0, then the probability that Sn is equal to lambda 0, this is converging to 1. And now let's take k larger than 1. So for k larger than 1, we have this computation. And now in this computation, what we see is that, well, this is fixed. This is converging to 1 as before. But now since Pn is converging to 0, this to the power k is converging to 0. This is converging to 1, and this is converging to 1. So the probability by the same equation, the probability that Sn is equal to k, this is converging to 0 for any k larger than 1. And this means that Sn is converging in distribution to the Poisson random variable with parameter lambda equal to 0. So we proved up to now that if this condition holds, then indeed Sn converges in distribution to a Poisson of parameter lambda, even in the case in which lambda is equal to 0. Now let's prove the converse. So let's assume that Sn converges in distribution. As we have seen, if Sn converges in distribution, this means that the probability that Sn is equal to q, to k, converge to q of k for all k in n0. Well, in particular, the probability that Sn is equal to 0 converge, and the probability that Sn is equal to 0, we computed, it's 1 minus Pn. So we need them all to be 0. Remember that capital N is equal to small n to the power n. And this can be rewritten as 1 minus n times Pn divided by n to the power n. So we know that this sequence converge. And as I claimed, if this sequence converge, this implies that n Pn converge to some lambda in 0 infinity. And therefore, we have that indeed, if Sn converge in distribution, then nPn converge to some lambda in 0 infinity, which is our claim. And once we know that this nPn converge to lambda, then we can obtain that Sn actually converge to a Poisson distribution. So this is an example in which a sum of small random variables, so that the sum of x and j from 1 to n, it's converging in distribution to a limit which is not a Gaussian random variable, but is now a Poisson. So it's a natural, well, there are many natural questions. The first question is, well, this is a natural question. What are the possible limits? So what are the possible distributions which are limits of such type of sum? So the precise question would be the following. Well, let's consider an array, xn1 up to xn, which are IID. Let's assume that Sn, the sum converging distribution, what is a possible limit for this sequence? So this is a question, and then once we characterize all possible limits, to find sufficient conditions in order for such a sequence to converge, and maybe we can relax not asking them to be identically distributed, but just independent, and still keeping, and remember that, we'll always be keeping the assumption on the uniform smallness of these random variables. So this is the question I want to address now. But before I address this question, let me compute the characteristic function of a Poisson random variable. And I will reformulate what we need. So before we proceed, let me compute. So let me assume that x, it's a Poisson random variable with parameter lambda, and let me compute its characteristic function, because these characteristic functions will appear in our analysis. So this is, remember, the expectation of exponential I tx. Now x takes values in n0, so this is a sum for k larger or equal to 0. The probability that x it's equal to k, it's lambda to the power k, k factorial exponential minus lambda. Let me assume now that lambda is strictly positive, and then if x takes the value k, this is equal to exponential I tk, and so you see that this is a sum. You have lambda times exponential it to the power k, and that will give me the exponential of lambda times the exponential of it minus 1. So this is the characteristic function of a Poisson with parameter lambda strictly positive. I want to generalize this distribution and say that x has a Poisson distribution with parameter a and lambda. So here a it's strictly positive and lambda it's strictly positive. So if the probability that x it's equal to a times k, it's given by this equation, by lambda to the power k, k factorial exponential minus lambda. So the difference here is that instead of taking values on the integers, they will take values on multiples of a. So this random variable takes the value 0 or a, 2a, 3a, and so on. And it takes these values with these probabilities. So if now I compute the characteristic function of this random variable, so maybe let me write it as a function of lambda and a. So phi a lambda of t, well, we'll get exactly the same expression. So it's a sum for k larger than 0, the same probabilities, lambda k, k factorial exponential lambda a. But now x, it's taking value a times k. So that will be exponential I t a k. And by the same reason, what you see is that you get here that this is equal to the exponential of lambda times e a t minus 1. So this is the characteristic function of a Poisson of parameter a lambda. And last computation I want to make, and I want you to keep them in mind. So let's assume that you have xj, which are a Poisson with parameters aj, lambda j. And say that j runs from 1 up. And maybe p is not well chosen. Let me call it L. And I want now the characteristic function of the sum of x1 plus xl. So these are independent variables where xj takes the distribution of xj is equal to a Poisson of parameters aj lambda j. So we know that f of x1 plus xl of t is just the product of the fxj of t, and we computed already the distribution, so that will give us that this is the exponential of a sum from 1 up to L. So the parameters are now lambda j, and we have I a j t minus 1. So if you understand lambda j as a weight, so this is an integral of this expression. So you can understand this sum as an integral of this function with respect to a measure, and the measure puts weight lambda j to the point aj. So keep that in mind, because these type of characteristic functions will appear in a second. So this is just a computation to have clear where these type of characteristic functions comes from. They will appear later. And now let us turn to the problem to say that assume that you have x1, xn1, xn iid. Assume that Sn converge in distribution to some S. Then we ask ourselves, what is the distribution of S? And this will be called the infinitely divisible, and which is the title of this lecture. So now we come to the infinitely divisible loss. So I'm taking an array of IID random variables, xn1, xnn. I will assume that Sn, which is the sum of x and j, it's converging in distribution to some S. And my question is, what is the law? What is the distribution of S? And before I give you a definition, the definition of infinitely divisible laws, let me give you an idea. So I'm assuming that Sn is converging in distribution. So if I take S2n, it's converging in distribution to our random variable limit, let's call it x. So this means that xn1 plus xn, x2n, sorry, plus 2nn plus x2n n plus 1 plus x2n to n, that this is converging to, in distribution, to our random variable x. So if I call this random variable y1n, and this second sum yn y2n, it's clear that yn1 and yn2 are IID. They have the same distribution. Right? Because, well, they are sum of IID random variables, same number of terms. So and what we know is that the sum is converging. So it's reasonable to expect that y1n will converge to a random variable y1, and that y2n will converge to a random variable y2. It's clear, since they have the same distribution, that y1 and y2 have the same distribution. Since they are independent, the limit will be independent, and therefore x, the distribution of x, can be written as the sum. So x, it's equal in distribution of the sum of two random variables with the same law, and which are independent. So if what I'm claiming is correct, so we have to check that if this large sum is converging in distribution, then each of these terms is converging also in distribution. But if this is correct, it will follow from this argument that x is equal in the distribution of the sum of two IID random variables, independent and identically distributed. And the argument which I just presented for 2 can be extended for k random variable. It's enough here to take kn, and here look for the first n, for the second n, the kth n, and the same argument will give you that x can be written, or the distribution of x, it's equal to the sum of k IID random variable. So this, I hope, motivates the following definition. So definition, and this is the definition of infinitely divisible law. So a random variable x has an infinite divisible law if and only if for all k larger than 1, or say 2, there exist k random variables, k1 up to kk, which are IID, and such that x is equal in distribution to y1k plus ykk. So this is the definition. We'll say that x, the law of x, is infinitely divisible, or if x has an infinitely divisible law, if for all k larger than 2, for k equal to 1, this is obvious, for all k larger than 2, we can find k IID random variables, which I'm representing by yk1 up to ykk, such that x is equal in distribution to the sum of these k IID random variable. So this is the definition. Now I will prove that the proposition I mentioned, that if Sn is converging in distribution to S, then S has an infinite divisible law. And then I'll give you examples of infinitely divisible laws. And in the next lectures, we will investigate what are these laws, and then find conditions for which this convergence occurs. So the plan of this lecture is the following. I will first prove that if Sn converges in distribution to S under this condition and the uniform smallest condition, then S has an infinitely divisible law, and then I will give you an example, and on the next lectures we will continue our investigation of these laws. So the proposition I want to prove is the following. Assume that xn1, xn are IID, that the sum Sn converge to some distribution n, where the sum is this sum. Then I claim that S has an infinitely divisible law. And so let's prove this result. So since Sn is converging, we know that S2n is converging in distribution to S. I will prove that S can be written as y21 plus y22, where y21 and y22 are IID, but the same argument applies for any k. So S2n converge in distribution to S. So this means that if, well, as I wrote before, x n 2n1 plus x 2n n plus x 2n n plus 1 plus x 2n 2n converge to S in distribution. And I want to define this as y1n, and this sum as y2n. Now, my claim is that y1n is tight. It's a sequence, a tight sequence of random variables. And to prove that y1n is tight, what I need to control is the probability that y1n is larger than some a. I want to fix an epsilon positive, and I want to show that there exists an a for which this probability is bounded by epsilon. So let me take the square of this quantity, and let's bound this quantity. So I'm fixing a. I'll choose a later in terms of epsilon. What I know is that y1n plus y2n, which is s2n, that this one is tight. It's tight because it converges. So we know that if a sequence converges in distribution, then it's tight. So, and therefore, the sum of y1 plus y2, it's a tight sequence of random variables. So let me take the square. Now, and in this argument, I want you to always think if you can apply it for k instead of 2. So keep in mind that what we really want is to prove this for any k. We are proving it to k equal to 2, but you'll see that the arguments apply to any k. So keep that in mind. So here I'm writing that as a power 2 just to use the fact that they have the same distribution to write this as the probability that y1n is larger than a times the probability that y2n is larger than a. And this comes from the fact that they have the same distribution. Now, by independence, this is equal to the intersection, so this is the probability that y1n is larger than a and y2n is larger than a. Well, but since S2n is the sum of y1n and y2n, if y1n is larger than a and y2n is larger than a, then the sum is larger than 2a. So this is less or equal than the probability that S2n is larger than a. And as 2n is a tight sequence, we can find a as a function of epsilon sufficiently large for that to be bounded by epsilon square. So we know that there exists a, which depends on epsilon, such that the limit sup of this expression is bounded by epsilon square. And this means that the limit sup of this expression is bounded by epsilon square, and therefore that indeed, well, we have a bound for y1n larger than a. The same argument applies, of course, to y1n smaller than minus a. You can repeat the same argument and show that you can find a new a such that the limit sup of this quantity is bounded by epsilon for that choice of a epsilon. And putting together these two expressions, what we conclude is that there exists a of epsilon by choosing the largest one such that the limit sup of the probability that y1n is larger than a, then this is bounded by 2 epsilon. And this guarantees that the sequence y1n is tight. So it follows, which is exactly our claim. So that proves, this argument proves that the sequence y1n is tight. So I will erase that. So y1n is tight. This means that y2n is also tight because they have the same distribution. Since this sequence is tight, we can find a subsequence which converge. So there is a subsequence y1 n prime which converge to y1. And from this subsequence, since y2 and its tight, we can find a subsequence for which n second of converge to some y2. And since this is a subsequence, we also know that y1 and n prime prime converge to y1 in distribution. And now we can conclude our argument, because we will take here n double prime, n double prime, both converge in distribution. So this one converge in distribution to y1, this one converge in distribution to y2. But now, since they are independent, the sum converge in distribution to y1 plus y2, but the sum also converge in distribution to S. So we have that this sequence, y1 n double prime plus y2 n double prime, converge in distribution to S, and converge in distribution to y1 plus y2. So this implies that y1 plus y2 it's equal in distribution to S. And this is exactly what we wanted to prove, because y1 and y2 are independent, because this sequence is independent from that one, and they have the same distribution, because for each n double prime fixed, they have the same distribution. So this is a sequence. Well, these are two random variables which are ID, and therefore we proved that indeed the distribution of S can be written as the sum of two independent, identically distributed random variables. And this argument, as you have seen, can be extended for any k, and that proves that indeed has the random variable S, the limit, has an infinitely divisible law, which means that any limit has to have an infinitely divisible law. So now what remains to be done is, well, to investigate which are these laws. So I'll give you now some examples of infinitely divisible laws, and in the next lectures we will investigate more closely this problem. So let me give you some examples. And so let's assume that X has an infinitely divisible law. Let us represent its characteristic function by phi of X. So this means that for all k, X it's equal in distribution to X, let's say k1 plus X k k, and these are ID random variable, so this means that the characteristic function phi of X at t, it's equal to this characteristic function, but this means that, so let me call phi k of t the characteristic function of phi x k1. They are ID, so they have the same distribution. In particular, they all have the same characteristic function. And since, well, this is equal to f, the sum xk1 plus xkk of t, but this is equal to the product. They have all the same law, so this is f k t to the power k. So if you want to show that random variable x has an infinitely divisible law, you have to show that for each k, phi x of t can be written as phi k t to the power k, so that there exists a characteristic function phi of k such that phi x of t is equal to phi of t to the power k. Right? And if this is true, then this means that the distribution so what I'm claiming is that x, so this is a remark, an observation, x has an infinite divisible law if and only if, for all k, there exists a characteristic function phi of k. So phi of k has to be the characteristic function of some distribution such that phi x of t is equal to phi k of t to the power k. Right? We have seen one direction. So if x has an infinite divisible law, this means that x is equal in distribution to the sum. So if you take the characteristic function of x, it can be written as fk t to the power k, where the characteristic function f phi k is the characteristic function of xk1. Now, so this proves this direction. So now let's just check the other direction. If phi x t is equal to phi k t k for all k larger than 1, phi kt is the characteristic function. So this means that phi xt is equal to the characteristic function of xk1 plus xkk, where xk1, xkk are IID random variable, and these are the random variable characterized by the characteristic function phi of k. So we know that the characteristic function phi of k characterizes the distribution. So these random variables are the ones whose characteristic function is equal to phi of k. Now we have this identity, so we know, since the characteristic function characterizes the distribution, that x is equal in distribution to this. And this means that, well, this holds for k, but since this is true for all k, this means that x is an infinitely divisible law, or has an infinitely divisible law. So that proves this observation. So in order to prove that some distribution is infinitely divisible, we need only to check that this is possible. So let me take one example in which the x takes a value t with probability 1. So this means that x is concentrated on t. So now if you compute the characteristic function of x, of t, well, this is exponential I. Of course, t, it's not a good idea, so let's assume that x takes the value b with probability 1. So this is I b t. So this is the characteristic function of the random variable. Now fix k. Let me take phi k of t, the power 1 over k of this expression. So this will be exponential I b divided by k times t. My first remark is that indeed phi k is the characteristic function, because phi k is the characteristic function of the random variable which takes the value b divided by k with probability 1. This is what we have seen, right? If it takes the value b, then its characteristic function is this one. If it takes the value b over k, the characteristic function will be equal to that. So indeed, this is a characteristic function, and it's clear that phi x t is equal to phi k t to the power k. And therefore, this condition is satisfied, which means that x has an infinitely divisible law. So this is a first example. If you have a random variable which is concentrated at one point, its law is infinitely divisible. So this is example 1. Now example 2, it's the Gaussian. So let's assume that x has a mean 0 with a Gaussian random variable with mean 0 and variance sigma square. So this means that phi x of t is equal to exponential minus t square sigma square divided by 2. So this is the characteristic function of the Gaussian. So now let's consider k equal to 1, and we wish to write f xt as fk of t to the power k. This means that fk of t has to be equal to the exponential of minus t square sigma square divided by 2 times k. But this is exactly to take exponential minus t square sigma divided by square root of k square divided by 2. So this means that phi k is the characteristic function of a Gaussian random variable. If I look at this formula, so this is just to take sigma square instead of taking sigma square, taking sigma square divided by k. So if I take phi random variable which has Gaussian random variable which has mean 0 and variance sigma square divided by k, then if y has distribution, then phi of y of t it's equal to phi k of t, and this means therefore that phi k it's indeed the characteristic function of a random variable, and since phi x of t it's equal to phi k of t to the power k, by this observation this means that Gaussian mean zero Gaussian random variables have an infinitely divisible law. So this is a second example. So let me give you a third example now. So example, Poisson of parameter lambda. So let me take x, and let's say that lambda is strictly positive, so let's take x a Poisson of distribution lambda. So let me write it in this way. So we can compute the characteristic function of this random variable. We compute it at the beginning. It's given by exponential lambda e t minus 1. So this is the characteristic function of a Poisson of parameter lambda. We computed at the beginning of this lecture. Now I want to write fxt as some characteristic function phi k of t to the power k. So this means that phi k of t has to be equal to this to the power 1 over k. So this is the exponential of lambda divided by k of exponential it minus 1. And it's clear that if I take y a Poisson of parameter lambda divided by k, then phi of y of t it's equal to phi k of t. Right? Because if y has a Poisson lambda over k, by this formula, its characteristic function, its exponential lambda divided by k times this expression. This is exactly what's written here, and therefore phi of y it's phi of k. Therefore this means that phi of k it's indeed the characteristic function of a random variable. Since we have this identity, this means that x it's an infinitely divisible law, and this proves therefore that the Poisson distributions have also an infinite divisible law. So a fourth example is the following. So let's take x1, x2, IID random variables. Any distribution, but identically distributed and independent. And now let me take n, a distribution which is Poisson of parameter lambda, and n is independent from the sequence xj. And now let me define a new random variable, z, which is the sum, the random sum from 1 up to n of xj. So if n is equal to 0, this means that z is equal to 0. If n is equal to 1, this means that z is equal to x1, and so on. So I claim that z has an infinitely divisible law. Mind that here I'm not assuming anything about the distribution of x1. So to prove that, let's compute the characteristic function of z. So this is the expectation of exponential I t of z. Now z, it's exponential of the sum from 1 up to n of I t xj. Now, since n it's independent from xj, this is, we can rewrite this as a sum for j larger than, well, 0. The probability that n it's equal to j. So here I'm dividing this expectation, placing here the characteristic function that n it's equal to j, or k, let's say k. So let's call that k. Now, since n, so I'm summing over all possible values of k, so k larger or equal to 0. So I'm placing, this is bounded by 1, so I'm allowed to move the sum outside of the expectation. Then, since n is equal to k, I can replace this n by k. Now I have here the product of two functions of independent random variable, so I can rewrite this expectation as the expectation of this expression times the expectation of this one, but this one is the probability that n is equal to k, which is what I wrote over there. And then the expectation of I t, the sum from 1 to k of xj. Right, so this is what I did. I first placed the characteristic function that n is equal to k by summing over all possible values of k. I moved this sum out of the expectation. Then I replaced n in this sum by k. After doing that, I had the independence to write this as the expectation of this indicator function, which is the probability that n is equal to k, times the expectation of this one, which is what I wrote there. Now let me use the fact that the random variable xj are IID, so that will be equal to phi x1 of t to the power k. And let's write what is the probability that n is equal to k. So this is lambda to the power k divided by k factorial exponential minus lambda. And now you see that you have lambda times phi x1, so this is equal to the expectation of lambda phi x1 t minus 1. So this is the characteristic function of this random variable z. So this is phi of zt. Right? Now I computed phi of zt, and I want to show now that z has an infinitely divisible law by using this observation. Phi zt, I want to rewrite it as phi k of t to the power k. So this means that phi k of t has to be equal to the power 1 over k of this expression. So this is exponential lambda divided by k of phi x1 t minus 1. And this is clearly the distribution the characteristic function of such a random variable where instead of taking n to be a Poisson of parameter lambda, I take lambda divided by k. So I take n, a random variable Poisson of parameter lambda divided by k. I define z by this formula. I get phi k of t as the characteristic function of this new random variable. So phi k of t is characteristic function of a distribution associated to the distribution, and therefore by this observation, indeed, z has an infinitely divisible law, and this was the last example of this lecture. So in the next lecture, we will investigate it more closely, what are the infinitely divisible laws, and what are, and find sufficient conditions for the sum Sn of independent random variables to converge to something which will be an infinitely divisible law.